In this video, we are starting our section on sequences and series. So in this video, we're going to talk about what a sequence is. So we'll define what it is and determine what does it take for a sequence to converge and diverge. Over the next few videos, we'll introduce what a series is, when do they converge and when do they diverge, and look at a couple of specific examples of series, which are called geometric and telescoping series. But let's start first with sequences. So a sequence is an ordered infinite list of numbers. So that means there's some order to the terms, and it goes on forever. So there's some first term, A1, some second term, A2, and then it keeps on going. So a common notation for a sequence is there might be some formula for the sequence, I'll call it A sub n, and you write it in these curly brackets. So let's look at an example. Let's say I have the sequence A sub n given by this formula, which I can also notate in my curly brackets. I want to list the first three terms of the sequence. So I first want to, there's one quick typo here. I didn't specify where does n start. So n, I'm going to specify is greater than or equal to 1. All right, so when I plug in values for n, I'm going to start off with n equals 1, and we only plug in integer values for n. So when I plug in n equals 1, I get a sub 1, and I'll get 1 and then minus 1/2, because that's what negative 1/2 to the 1 is. Well, I simplify this to 1/2. That means the first term of this list of the sequence is just 1/2. Okay, what about if I plug in 2? So a sub 2 would be, I get 1, and then negative 1/2 squared, I'll get positive 1/4. Okay, so now this simplifies to 5/4. So the first term was 1 minus a little bit. The second term is 1 plus a little bit. If I plug in 3 to get my third term, I'll get 1 minus 1/8. So this is going to be smaller than 1. So overall, that's 7/8. Okay, so I got the first three terms of my sequence. They're all kind of close to 1. This one's less than 1. Then I go bigger. Then I go less. Because I keep sort of alternating. Am I adding something to it or subtracting, depending on is this n even or odd? So now what I want to do is plot the first few terms of this sequence on a graph and then use that to make a guess for what the limit of it is. So let's draw some axes. I will draw some axes, and the horizontal axis I'll call n, what I'm plugging in, and the vertical axis a sub n, like what's the value of the sequence. So I'm plugging in things like n equals 1, n equals 2, 3, and I'll also put 4 on here. And then all these outputs are kind of close to 1, so I'll put a tick mark at 1. And I know a sub 1 is 1/2, so when n is 1, the output's 1/2. When n is 2, the output's 5/4, which is bigger than 1, so I should draw something above 1. And then when I plug in 3, I get 7/8, which is below 1, but it's closer to 1 than this value was. If I kept going and I did A4 is going to be, it turns out it's 17/16. I'll get 1 plus 1/16. So that's now above 1, but even closer to the 1. So it's above 1, but even closer to it. So it seems like these terms are getting like closer and closer to 1 as I go further and further out. So I'm going to put this little dashed line here at 1, and that seems to be like the limit of the sequence. And there's a conceptual reason why that is. So I can notate the limit of the sequence in this way, say the limit as n approaches infinity of my formula. Conceptually, that seems to happen because, well, this thing, the bigger n gets, I end up getting like 1 over like a really big denominator. It might be positive, it might be negative, depending on if n is even or odd. But overall, that makes this whole part get really close to 0. And then 1 plus something very close to 0, well, that just makes the whole thing very close to 1. So conceptually, that's why I expect the whole thing to be very close to 1. Let's make this more precise. So I'm going to give a definition here, which says a sequence converges to a number L. So in this case, L is 1. That's what I think it converges to. If for all, I'm going to introduce this Greek letter, epsilon. So epsilon, this is this Greek letter. If for all epsilon that are positive, that are bigger than 0, after some point, all the terms in my sequence lie in this interval that starts at L minus epsilon up until L plus epsilon. So, okay, what does that mean? I'm going to zoom in here a little bit. What that means is, so this epsilon is a distance away from L. So if I go some distance epsilon up, and I go the same distance epsilon down, that's going to put me at, this number down here is 1 minus epsilon, and this number up here is 1 plus epsilon. Now what I'm going to do is at each of those tick marks, I'm going to draw dotted lines, and draw a dotted line here as well. And what this does is this creates this little window, and I call this my epsilon window. And what the definition is saying is, okay, is there some point after which all the terms in the sequence are going to be within this epsilon window? And the way that I've drawn the graph, well, the first point is not. The second point also is like just a little outside, but then after that, we're all inside. Okay, so this epsilon window checks out. But that's not enough for the definition. The definition says, well, this needs to happen for any epsilon greater than 0. So I just picked a particular epsilon, but what if I made this even smaller? If I had an even smaller epsilon window, would it still work? And it turns out that, yeah, even if I had a smaller one, as long as I go far enough out, like maybe I have to start at like n equals 6, but as long as I go far enough out, eventually the terms will get close and closer to 1, so that no matter how small this epsilon window is, it seems like, yeah, there comes a point after which all the terms will lie within it. Okay, and that's what this definition is saying. No matter how small we make the epsilon window, after some point, all the terms are going to be within the window. And when that happens, I can write the limit of my sequence equals L. On the other hand, if there doesn't seem to be a value that the terms get really, really close to, then we say the sequence diverges. Okay, so I want to explore this epsilon definition a little bit more, because this is something where, especially if you take more math classes, you'll see this quite often. So I think it's helpful to play around with it. So let's suppose that epsilon was 0.01, which is 1 over 100. So I'm going 1 over 100 up, 1 over 100 down. Find a value of n such that once we reach it, all the subsequent terms of the sequence are within 0.01 of the limit. So all the terms are going to be within, if I go 0.01 up or 0.01 down, well, that puts me between 0.99 and 1.01. How far do I have to go to guarantee that? Well, so what I notice is the thing that kind of dictates how far from 1 I am is how big is this term? So what I need to make this happen is I need my negative 1/2 to the n. And I don't care if it's negative or positive, if I want it to be within this value. So I'm just going to absolute value it to guarantee it's positive. I want that to be less than 1 over 100. So how big does n have to be to guarantee that? Well, it turns out it's got to be 7. If I were to do negative 1/2 to the 7 and then absolute value it, I get 1 over 128. Okay, and that is less than 1 over 100. So once I reach n equals 7, all the terms after that, they are going to be within 1 over 100 of away from this limit value, away from the 1. Okay, and I can imagine that I could pick any other value for epsilon, even smaller. But if I made it smaller, I'm just going to have to make this exponent get larger to guarantee that eventually I'll get that small. Okay, and there we have it. That is our intro to sequences.